We are given a resistor network driven by a 1 mA current source with a 1 kΩ series resistor. Looking closely, the central interconnected loops form non-separable bridge meshes, making delta Y transformation mandatory. First, look at the outer right corner. Node 5 has no other external connections, meaning the 2 kΩ and 6 kΩ resistors are in series, totaling 8 kΩ. This 8 kΩ branches directly in parallel with the 8 kΩ diagonal resistor between node 3 and node 4. 8 parallel 8 simplifies to exactly 4 kΩ. Step 2. The top mesh formed by nodes 1, 2, and 3 is an equilateral delta of 3-4 kΩ resistors. We transform this delta into an equivalent wire star network. Each leg of the star network evaluates to 4 times 4 divided by 12, which is 4/3 of a kΩ, connected to a new central star node. Now node 3 only connects the top star leg and the right 4 kΩ branch in series. Combining them gives 4/3 plus 4, which equals 16/3 of a kΩ directly from the star center to node 4. Next, the bottom left loop between ground node 0, node 2, and node 4 forms another delta of 3-4 kΩ resistors. Transforming this delta to Y gives 3 branches of 4/3 of a kΩ each. Between the top and bottom star centers, we now have 2 parallel paths. 8/3 kΩ on the left and 20/3 kΩ on the right. Their parallel combination gives 40/21 kΩ. Adding the series top branch, parallel core, and bottom ground branch yields a network resistance of 32/7 kΩ. Including the 1 kΩ series resistor at the source, total equivalent resistance is 39/7, or 5.571 kΩ. In summary, the total equivalent resistance seen by the 1 mA current source is 39/7 kΩ, resulting in a total circuit terminal voltage of 5.5714 volts. This completes the full delta Y circuit reduction.